that was on the example bottom right. Indicates that that irrational function has no horizontal asymptote. Remind me why?
Because the degree is higher on the top than on the bottom.
Degree on the top is higher than the degree on the bottom. But that degree difference is like only 1. So, like that seems to suggest that this is like a degree 1 polynomial, kind of. It's not, like it's got a vertical asymptote. But it doesn't have a horizontal asymptote, but it does have something. Let's talk about how you find the asymptote that it does have. Nice. All right. So, let's talk about finding non-horizontal asymptotes. And the trick you need is polynomial long division, but let's just list the things we can find. Is this the same function as was on the previous page? Okay, that's good. No guarantee that I would have set that up correctly, but it should be. Let's find its things. It has a y-intercept. Where is its y-intercept? Slash, should I find the y-intercept? Okay, cool. So just tell me what the y-intercept is. -1. And I'll be like picky and say, well, it's 0 and -1, but you get it. You got that by just plugging in x equals 0, yeah. X-intercepts. Maybe it takes more effort to find them. Should I go through finding the x-intercepts? Okay, seeing at least one head nod. I will. If you do it on your own, you'll probably do it faster. So, to find the x-intercepts of a rational function, you set the numerator equal to 0. I guess here I'm like blowing by the fact that the numerator and denominator are, they have no common factors. So, doing that, x squared plus x plus 1 equals 0. Looks like a quadratic formula type of situation. I guess we could check the discriminant to just see if it has irrational roots at all. Nope, real roots at all. Doing that, let's see, just using the quadratic formula, x equals -b plus or minus the square root of b squared minus 4 times a times c all over 2a. What can you tell me about what's written there?
They're imaginary.
Well, they're complex, right? Imaginary means they have 0 real part. So, but still, the point stands, like, they're not things we're going to see on a real graph anyway. No real x-intercepts. Vertical asymptotes. And I guess same question. Like, either you'll tell me what they are or I can find them. Should I do the walk?
Yeah.
Cool. I hear a 1/2. Tell me how you got that 1/2.
You take the bottom and find it.
Nice. So you take the bottom, the denominator, and set it equal to 0. So to find the vertical asymptote, set 2x minus 1 equals 0. Yeah, solve that for x, you get x equals 1/2. It's a vertical asymptote, so I should indicate it like a vertical line. So far, so good. Horizontal asymptotes.
There.
Yeah, there are none. That's on the previous page. So it doesn't have any horizontal asymptotes, but it does something interesting when you plug in a big x value. And let's see what it is that it does. I want this one. Okay. So let's graph that then. X squared plus x plus 1, close parentheses, divide by 2x minus 1. So let's see, an asymptote, a non-vertical asymptote, is like what happens when you look very far along the graph. You look really far along that graph, what does that thing now look like? A straight line? It looks like it has some slope. by looking at this, can you eyeball about what the slope is? You could draw 2 points on it and see if you can estimate the slope. We'll get the slope in a moment, and then we'll see if it agrees with the picture. So let's talk about how to actually find that line. The way we're going to find that line is we are going to rewrite this rational function in a manner that looks like a line plus something that gets small. And the way we'll do that is by doing some polynomial long division. Can't use synthetic division here because there's a 2 in front of the x in the denominator. So let's do this polynomial long division. 2x minus 1, let's divide that into x squared plus x plus 1. All right, so I guess we just have to do it. What do you need to multiply that 2x by to get x squared? Let's see, you need to raise the power on the x by 1, so there better be an x, and then you need to turn that 2 into a 1. What do you multiply 2 by to get 1? 1. So first entry is 1/2 x. And now you know what I'm going to do. I'm going to multiply this by that and subtract the result. So I'll play the game where I distribute using the fact that I have erasable pens. So it'll be negative 1/2 x times 2x is x squared. I know that's what it should be. 1/2 x times minus 1 is minus 1/2 x. But then you have to distribute the negative sign. Negative sign goes there. And this minus becomes a plus. All right, that seem okay? And now you just keep on going top to bottom. X squared minus x squared is 0. That's what I knew it should be. X plus 1/2 x is 3/2 of an x. And I'll bring down the plus 1 just because I'll need it a moment anyway. Okay, so now we repeat. What do I need to multiply 2x by to get 3/2 x?
3/4.
3/4.
Just 3/4, yeah.
Yeah. So I need to get the 2 down to 1/2, so I need to divide it by 2 twice. So divide by 4. I need to get the 3 to show up, so I need the 3/2. If you need to, then off to the side, you can say, well, shoot, 2x times what equals 3/2 x? And all right, the x's cancel. You need to divide the 2 to the other side. Blah equals 3/4. All right, so let's put that 3/4. And in some sense, that's enough information to do what we want to do. But I am going to find the remainder term because that will let me actually put an equal sign in the next line. So let's repeat. 3/4 times 2x, and I'll need to subtract it, so minus, and then I'll put in the parentheses. 3/4 times 2 is 3/2, which is what I want it to be, minus 3/4. Now play the same game, distribute the negative sign. That was supposed to be in pink. So you can erase the parentheses, putting a negative in front of 3/2, and changing this minus to a plus. All right. 1 plus 3/4 is 7/4, or 1.75 if you like decimals better than you like fractions. And at this point, 7/4 is a constant that's lower degree than the x, so that's just a remainder term. All right. So let's write down what this means. This means that this fraction is equal to the result of division. 1/2 x plus 3/4 plus the remainder term, 7/4 over 2x minus 1. Because that's what the remainder term means, right? Like if I ask you to do 72 divided by 5, you end up with a remainder of 2. That tells you that there's a 2/5 at the end. nice. So, let's think about what this is. So here's like a linear function. Here is a remainder. And this remainder term, 7/4, divided by 2x minus 1. If you want to plug in a big input for x, because that's what you want to do when you want to find horizontal asymptotes, it's really small. If you plug in like a 10-digit number, you have 7/4 divided by 2 times a 10-digit number minus 1. That's basically 0. So this piece is really small when you plug in something big. So this whole fraction, which remember we just got to be equal to the linear term, 1/2 x plus 3/4 plus the remainder term, 7/4 divided by 2x minus 1, is basically the same as 1/2 x plus 3/4. So when you want to find a slant asymptote, there will always be a slant asymptote whenever the degree of the numerator is 1 bigger than the degree of the denominator. The degrees want to cancel. In order to find that slant asymptote, you have to do some polynomial long division. That feel okay? And let's just check this. We can see if this is correct now using like Desmos for stuff. So let's first check if this equality is correct. If that's correct, because whenever you do polynomial long division, that's a lot of moving parts. Did anyone notice me make an error during the process? I certainly didn't intentionally make one, but I do things wrong all the time. Cool. Let's check it. 1/2 x plus 3/4 plus 7/4 divided by 2x minus 1. Yeah, that looks right. Now let's check if this slant asymptote we found is correct. 1/2 x plus 3/4. That green line seemed like it gets pretty close to the graph in question. Yeah, and if you really want to check, then scroll really far along, maybe zoom in some. Yeah, those two look like they're basically on top of each other. Neato. That feel pretty good? If you want to find a slant asymptote, do polynomial long division. Oh, let's maybe notice one more thing. The slope of this line, you could have, in fact, known that before you even started. That 1/2 came from that 1 divided by this 2. So you know the slope of the slant asymptote before you even begin. Yeah. So I think let's do at least one example where we put all this together. Here is a graphing exercise. Let's sketch the graph. Well, let's see. I think we're either going to do this one or the one on the next page. So let's take a look at that one and just ask the horizontal asymptote question. Does that thing have a horizontal asymptote, a slant asymptote, or neither? What's the degree of the numerator of this fraction? 2. There will be an x squared when you FOIL it out. What's the degree of the denominator? Squared. Also 2. So it has a horizontal asymptote. I'm going to flip to the next page real quick. How about that one? Horizontal asymptote or slant asymptote or neither? Slant asymptote. It's degree 2 on top, degree 1 on bottom. So we'll do one or the other right now. Would you rather see one that has a horizontal asymptote or slant worked out? Horizontal asymptote? Slant asymptote? Okay, I think it was roughly 1 to 1 out of a room of 46. Yeah, so that's a good target. We'll do the first, then we'll see if there's demand to do the second. So let's just walk this one out all the way through. So I want to graph this in a manner that has the correct local behavior near all the intercepts and all the asymptotes. Is positive and negative in the correct places. Has the right horizontal asymptote. So, let's start with this. Let's find the x-intercepts and y-intercepts. Is that like really easy to do based on how it's written? Do people want me to do it? Cool, then I will. So, I guess I'll start with the x-intercepts because that comes first. How do you find the x-intercepts of a rational function? You set the numerator equal to 0. Because do the numerator and denominator have any common factors? Nope. It's even already factored for you, so it's easy to check. So to find the x-intercepts, you need to set x plus 1, x minus 2 equal to 0. Oh, cool. Does that look like it's basically automatic to solve that for x? Yeah, you don't need the quadratic formula or anything. It's already factored. So that splits to x plus 1 equals 0, or x minus 2 equals 0, x equals negative 1, or x equals 2. So the x-intercepts are negative 1, 0, and 2, 0. Let's dot those. Negative 1, 0, 2, 0. How do you find the y-intercept? Should I find the y-intercept? Cool, then where's the y-intercept?
0, 1.
I hear a 0, 1. Do I hear a second? I hear a second. Cool. Should I do? I didn't see any hands go up, but should I? Okay. All right. Cool. All right, so we have the intercepts. Let's find the asymptotes. I guess vertical asymptotes are the first in the list. How do you find the vertical asymptotes of a rational function? You just need to see when the denominator is 0. When you divide by 0, you get a vertical asymptote, unless there's a 0 in the numerator to cancel it. So, let's find the vertical asymptotes. You find the vertical asymptotes by setting the denominator equal to 0. X plus 2 times x minus 1 equals 0, Gesundheit. Again, does that look like an easy thing to solve? Yeah, what do you get?
Y equals 92 and y equals 1.
Except x's. Vertical asymptote, so it's x equals.
X equals.
Nice. And so that says that these vertical lines are lines that the graph is going to get close to. So there's x equals negative 2. There's x equals 1. So there are some vertical lines that this graph has to get close to. Horizontal asymptotes. How do you find those? Or just where is the horizontal asymptote of this thing?
1.
At y equals 1? Why y equals 1?
They both have the same degree, so you take the coefficients.
Yeah, both have the same degree, so you can just take the leading coefficient. If you FOIL at the top, you'll get 1 as the leading coefficient, same in the bottom. The other strategy is when you want the horizontal asymptotes, you can ignore everything except for the biggest thing. So x plus 1, that's basically just x. X minus 2, that's basically just x. X plus 2, that's basically just x. X minus 1, that's basically just x. So yeah, horizontal asymptote at y equals 1. All right, so far so good. And even just based on what's drawn so far, do you think this thing is going to have to hit its horizontal asymptote?
Yeah.
To get that y-intercept, I'll need to hit that horizontal asymptote. So, now, I want this graph to be positive / negative in the correct places. And we have like a standard strategy to do that. You plug in some like sample values, decide whether the thing's positive or negative, and graph accordingly. So where are the places where the thing could change from positive to negative or negative to positive? It can change at the intercepts, at the x-intercepts, and at the vertical asymptotes. They're the places where the positivity or negativity could change. So I just need to pick some sample values, and let's try to be efficient. What's a sample value we could check that's less than -2? -2. We could do that? In fact, how many people I already have? What'd you get, positive or negative?
Positive.
Positive. Here's what I'll propose. Instead of plugging in -3, I'll plug in -3 trillion. Because that means that like the +1, -2, +2, and -1 basically don't matter. It's at the it's at the horizontal asymptote, which is positive. So you can avoid the computation. So when x is less than -2, y has to get close to the horizontal asymptote, which is 1. So that means y has to be positive until it gets to that vertical asymptote. So it goes from positive, it needs to get close to the vertical asymptote. Feel good so far? Other than the fact that it's not